All right, we're back. CJ and I have got our books, and Dr. Lou with us. Smitty ain't got his book, but that's all right. Here we are. Here's Larry.
All Things Unexplained. Hosted by Dr. Mounce.
Let's face it, we were always ready to roll without him anyway.
CJ Derringer.
Ain't nobody perfect, right?
And Smitty Neebs.
I've never planned out hardly anything my whole life. I just freeball.
Featuring Cajun Man.
I'm just old nobody, somebody looking for somebody.
Hello, all you unexplained ones out there. We have an exciting show for you. He's back, ladies and gentlemen. It is author, podcaster, professor, astrophysicist, the man who does it all. It's Dr. Chuck Blue. Welcome back to our show.
It's
Good
so
to
good
see
to
you.
be back. Thank you so much for having me. Thank you. Can't wait for today. It's
And
awesome.
honestly, the timing of having you back on our show could not have been more fitting. Number one, we have all of these incredible images that have come out from the James Webb Telescope. And number two, Comic-Con is back. It is back with
Woohoo.
Avengers. So,
Nice one.
before we get started, why don't you tell us real quick about the book that you have written? We talked about it on a podcast
Oh,
before, but The
yes.
Cosmos Explained.
Right. It's a book that I wrote, published by Ivy Press in the UK. Actually, it turns out that my daughter, who happened to be in Paris recently, actually saw it in a bookstore in France. So I'm very excited that it's overseas as well as the United States.
That's
But
a big deal.
which is yeah, it is, and it's especially cool because it's half pictures. It's a story of the universe, like from the Big Bang to the present day and beyond, kind of like in a timeline, a history, but not wrapped up in jargon or all in words. We've tried to find a way to tell the story without dumbing things down, but actually speaking in a language that we all can understand without taking years and years of math and science classes. And so it's really a lot of fun. I enjoyed a great deal, and we made sure that the pictures weren't just flashy, but actually had some scientific information, some knowledge we can convey, because we all learn from all kinds of different ways, not just words, not just being told stuff, but actually seeing through the art too. So I'm really happy with the book. I really enjoyed it, and thank you so much for letting me have the chance to talk about it.
Yeah, we honestly loved it. When I read it, and I know Tim read it as well, it just is very easy to understand. And just like when we had you on the podcast last time, afterwards, everybody said, wow, he made really complicated things attainable to understand. So thank you for that. And where can people find your book?
Well, it's pretty much in bookstores everywhere, Amazon, I guess, but there are many, many other places, and in bookstores. Just call and ask and find out. The publisher's name is Ivy Press in the United Kingdom, so maybe from there it can latch out to bookstores all around the world, including apparently France, which is kind of cool.
Okay. Good. Yes. Well, wonderful. Everybody go
Viva
pick
la
up a copy. It
France.
is really great. Yes. Okay. So when we knew you were coming back on this show and you had mentioned, let's talk about some of the James Webb Space Telescope. Tim said to me, this is like his Super Bowl. Like, this is what astrophysicists wait for, is images like these. So before we dive into each one of them specifically, tell me what your initial thought was when they started releasing some of these photos.
My jaw dropped. My heart skipped a beat. I mean, what additional metaphors can we use about like delightful surprise, right? The deal is this: these telescopes are amazing, and my colleagues who work on them, they spend good chunks of their careers on these, right? The James Webb Space Telescope was first conceived by my colleagues back when I was in graduate school, right, in the 1990s. So these folks spent a quarter of a century of their lives getting this thing out there. And during that time, technology has changed and improved so much. And this is an amazing instrument in numerous reasons. But one of the most cool reasons is that it views things by detecting the heat that comes from them rather than the visible light. So every image you see from the James Webb Space Telescope, almost without exception, are things we could not see with our eyes. But instead, they might be something you might see through infrared goggles. But you know how infrared goggles are like fuzzy and kind of weird colored and stuff like that? We have been able to take those images and make them as sharp as any Hubble Space Telescope image, as any ground-based visible light image, and you can see the universe in a way that we never have before. Never. It is just remarkable, and I'm so happy. All these images are so beautiful, so well done. Can't wait to talk about them to anybody who wants to hear about it. It's basically the story.
Yeah. So they are incredible. Now I have to ask, I was trying to figure this out. What we are actually seeing that's being released from NASA, that's sort of is that an artist's rendering of the science? Or what are we looking at exactly when we see these photos?
These photos are actual real photographs. They're
No.
digital cameras, basically. Yeah, they're not artist renditions.
I cannot believe
The-
that. Okay, now my mind really is blown.
Yeah, they are
I didn't
actual
think
digital
that at all.
photographs. Yeah. Imagine a telescope 20 feet across. Okay, 20 feet, not just like one of these things you hold in your hand, right? 20 feet across, taking pictures using infrared light. And what they do is they'll take a picture in infrared band 1 and map it with like red, and then infrared band 2 and map it with green, and infrared band 3 and match it with blue. So you get an RGB translation of this infrared stuff, but it's all real photographs. And the last picture, I know, it's amazing. And the last picture,
it's amazing.
The final picture that was released that might have gotten a little less press, but I found even more astounding than the pictures themselves that are so beautiful. It was the spectrum. Do you remember that there was a planet outside our solar system called WASP 96b or something like that? And what had happened was that they couldn't get a picture of it because even the James Webb is not powerful enough to actually take a photograph of a tiny planet. Well, tiny, it's the size of Jupiter, but it's a planet orbiting another star, trillions of miles away. So what instead it was able to do was it took a picture, fuzzy, of the light coming through the atmosphere of this planet, and then broke down this fuzzy atmospheric picture into its component colors, producing something called a spectrum. And what happens is that spectrum, again, is infrared, okay, which means that we could never see it with our own eyes. But by looking at the spectrum, they were able to confirm, my planetary science colleagues using the James Webb Space Telescope, that there is water vapor in abundance in the atmosphere of this exoplanet. I mean, imagine what that means, right? I mean, it's not a beautiful, pretty picture of forests and things like that, but we have absolute confirmation now that on a planet other than something orbiting our own sun, there is water vapor. We know when we think of water, we're like, oh, life out there.
Yeah.
So more than any of those other pictures that were beautiful and had incredible scientific content, which I love tremendously, this particular spectrum, which might not have seemed so beautiful right at the beginning, to me is the most telling of all, because it is the thing that most confirms to me that there probably is extraterrestrial life.
Oh, wow.
Yeah.
That's
wild.
amazing. Dr. Lou, I've heard Earth, that one of the enigmas I've heard about the Earth and our solar system is how we seem to be the only thing out there in what they describe as, I think, the Goldilocks zone.
Yes.
Of just the perfect combination of distance from a star, etc., atmosphere to, contain life such as us. I mean, is this the first time that there's another sign of a potential Goldilocks zone out there?
It's not the first sign, but it's a strong sign, if that makes sense. This particular planet is not within the Goldilocks region of its host star. It would be far too hot to have DNA-based life forms exist in a natural state. But what it shows is that planets outside our solar system have the same kinds of materials that we see here. We see water vapor in our atmosphere. We see water vapor in the atmospheres of the other planets that are in our solar system, right? Not all of them, but many of them. So that means that all those planets out there, which we are worried about whether or not they are unique, whether we are unique, whether they're somehow different from us in all cases, this is incontrovertible scientific evidence that we have a lot in common, way more in common than we are different. So perhaps in that solar system, there might not be a planet that's the size of the Earth and the mass of the Earth orbiting in a Goldilocks zone. But other places, there surely are likely to be. Would they develop life the way that we have here? It's impossible to tell right now. But the raw materials, the basic ingredients, the overall environments, the chemistry that could happen, that spectrum tells it all for me. I'm excited by it.
Well, Dr. Lou, would you call that pretty powerful evidence of things you talk about in your book, such as the very beginning of time with the Big Bang, the fact that something we're just discovering so far away is comprised of the same material as us? Doesn't that seem to be at least contributing evidence that everything at one time was, kind of this beyond description point of mass?
I think so. The time scales are very different, right? Because this planet is also roughly our age. It's in our own galaxy, so it's been 13.8 billion years since the Big Bang or thereabouts. So something that far away might not be able to give us a whole evidence of the entire universe from all that long time ago. But, we're still pretty far away. And if they can develop water vapor and we can develop water vapor, surely other places have water vapor, and maybe not even water vapor, but lakes and rivers and streams kind of like ours, and maybe little small furry creatures drinking from them. Who knows? I still don't think that there's enough evidence to say that anybody's ever visited us. But it's very clear to say that there will be someday when we're good enough, when we have developed enough technology, when we work hard enough at it, we will find something like life as we know it somewhere out there.
That's so exciting.
So some of that, I think, sir, we'll save for closed session.
Oh.
Gotta save that for closed
Don't
session.
give away too much. Okay, well, let's dive into some of these pictures. We do have the images, which my mind is still blown that they are actual images. The Carina Nebula is the first one we're looking at here. Beautiful photo, and it just there's these peaks and valleys and mountains, and I was reading on NASA's website that the tallest peaks in this image are 7 light years high. I can't even comprehend that.
And remember that, remember a light year is a length equal to about 6 trillion miles. Trillion, right? Sure. The distance from Earth to Pluto is only a few billion miles. So these are thousands of times larger than our entire solar system. But these peaks, don't let them fool you. Even though they look so, solid and stuff, they're like peaks in the clouds that we see passing by in the sky. Think about what clouds are here on Earth, like in an afternoon in July when thunderstorms are threatening, right? Those clouds are puffing by and they look like all kinds of things, right? They're like, oh, wow, I see a duck, or I see Godzilla, or I see Sasquatch, in these clouds. And you can look in here and see those things too. But if you were to fly up to those cloud edges, they would seem to melt away, because what you're really seeing is light scattering off of enough water vapor droplets and little particles and things like that it appears like it's a solid sheet. Okay, that's called the surface of last scattering. And so what happens here is indeed that. These are all clouds of gas and dust that are very sparse. At any given, say, cubic foot of that gas, you'll be lucky to find even 100 or 1,000 atoms total. It's not that dense. But because, as you said, they are trillions of miles high and long, the cumulative effect as we look through them produces these shadows and shapes, just like we see in the sky as we're watching thunderstorms approach. So that's what we're seeing here. And in the densest parts, the parts that are darkest, you are actually forming new stars in them. And we can't see them because they're obscured, they're enshrouded by this gas. But you see those little holes and pockets where there do seem to be stars shining through. Those are stars that were born thousands, maybe even millions of years ago, that then had enough light to shine through, to burn through that fog. And now we see them in their beautiful glory while we are looking at these clouds and going, wow, what is buried in there? What is hiding in these clouds that are so huge yet so dense once we get close?
That's amazing.
This image is so gorgeous. So, okay, so new stars are forming in this particular area. Do we think that that's happening in many, many areas of the universe? There's these star forming areas. I guess I didn't really ever think about new stars just forming all the time.
Yes, this is the star forming regions in the universe are plentiful. They don't show up everywhere. So, for example, in the Milky Way, there are many of them, and a few really big ones. Like Carina is a great example of a few big ones. But averaged over time, the Milky Way on average only makes about 10 stars a year. And most of them, 9 out of 10 of them, are faint, dim things that are less bright than the sun. So only every few centuries are stars brighter than the Earth, like Sirius or some of these other brighter stars in the sky, are they built. And only every few thousand years, really, are the really big, bright, beautiful ones built. And so you have to wait a long, long time to see the results of all these things happen. So even in this large-scale, beautiful star-forming region here with this nebula, you're still not going to see like stars just popping out. Like in our lifetimes, if even a few stars in the picture shown by the James Webb are born and appear, that in itself, it would be remarkable. And it is my hope that over time, if we keep watching this thing and like monitoring this or other star formation regions over many years' time, we will literally be able to watch a star being born. I would love to see that.
Yeah.
And this is impossible with visible light. It can only be done with this infrared light because the visible light would be blocked by all the dust that's impregnated within all of that gas.
Okay.
That makes sense.
It has a little bit of a Starry Night vibe, so that's fun.
Totally.
Okay, so
Beautiful.
next, moving on to Stefan's quintet. Did I say that correctly?
Yes.
So
You
this
did.
is 5
Mr.
galaxies
Stefan. Yes.
interacting
Right.
with one another. Okay.
The fifth.
So tell us the
the
importance
fifth
of
galaxy. Yes. All right. The importance is very basically this. The Milky Way is going to crash into Andromeda Galaxy, just like this, in about 5 billion years. Do we want to know what our galaxy will look like someday? This is basically telling us what one day our galaxy and Andromeda will look like. And again, the infrared detectability, the ability to detect the infrared is what's so stunning here. Pictures have been taken using visible light, optical light, of this quintet for decades. I've known about this for a long time. And what's happened is that when you notice that there's like this sort of whitish glow material outside, right? That's like the starlight that we could see with visible light. But the reddish streaks, which have been highlighted, using visual effect here, that's real photographs of gas floating around. Imagine, that Carina Nebula that you saw. Imagine it streaming all the way across an entire galaxy. Each of these galaxies isn't just a few light years across. They're 10,000, 50,000, 100,000 light years across. So imagine a Carina Nebula streaming across that entire thing. That's what we're seeing the gas flow. And along that gas
Wow.
flow, we're talking about the Milky Way forming, maybe 10 stars a year. In this case, these galaxies, as they're streaming and swirling, they may be forming thousands. So if we're talking about new galaxies, new planets, new life, this is where it's all happening. And that's just the beginning. This gas could swirl together, and instead of forming stars, form a supermassive black hole. They could become so hot that they could stream apart, blow away, form brand new tiny satellite galaxies. We call them tidal debris galaxies, off to the edges of the quintet. Now, that's cool. What's there? How do we form those things? This is just filled with amazing results. I'm so impressed. And you may know that my area of research actually focuses on colliding galaxies and supermassive black holes, as well as the star formation history of the universe. This is a quintessential demonstration of that.
A quintessential demonstration. I love that. Okay, so you were going to
Quintessential
say
That was an accident. That was an accident.
I caught it though. We're going to run with it. So you're about to say that the fifth galaxy, and I don't see it.
Yes.
So I see 4.
Well,
I was wondering
right.
that too.
The fifth, right. Notice the galaxy with the brightest red streaks just above it. Those are 2 galaxies in one. They are the ones that are colliding. And so those 2 form the 4th and 5th galaxies of the quintet. And that pair is what Andromeda and the Milky Way will look like 5 billion years from now.
Gotcha. It almost looks like a yin and yang symbol. Is that what I'm looking at? Those are the 2 that are...
You see it. Yep.
Yeah.
You see it exactly correctly. Yep.
Okay.
Well done.
That one kind of looks like a seahorse to me.
It does. I see a seahorse coming out of the top. Yeah.
I think you just
You're
named
right.
it the incursion, Smitty.
The Aquaman galaxy.
Yeah, there you go.
Okay. So the next image that we're going to see is the Southern Ring Nebula.
Yes.
And this is essentially a dying star, correct?
Yes.
And how its gas and dust are being expelled and giving us a chance to study its history.
This is what's cool about this, and remember, I don't do research in this area, so I can only give you the sort of broad strokes of this particular system. But let me tell you, do you notice carefully on the right-hand side that there are 2 stars in the middle, not just one?
Yes, I see that. Yep.
Right? There are 2 stars. You see, what the sun is going to do in about 5 billion years, right around the time we crash into the Milky Way, the sun is going to be almost a white dwarf, and it's going to blow off its outer layers, half of its mass, equivalent of more than 100,000 Earths, into this big puffy nebula that's almost looks like this weird planet thing, right, with gas streaming off of it. The problem is, it shouldn't look like that. How do you create this sort of organized spinning cloud thing if you're actually just ejecting your outer layers out into space? And it has long been hypothesized that many of these planetary nebulae are actually binary stars. And so it's the orbiting of the second star that organizes the gas into these swirling planetary nebulae. We haven't been able to see that because the centers of these nebulae are usually obscured for the visible light. It can only be seen in the infrared, plus it has to be seen from out in space where the distorting effects of the atmosphere cannot get in the way. And sure enough, when we use the James Webb Space Telescope to look at the system, you look at the near infrared and you see certain colors and certain shapes, but you can't tell whether there's 1 star or 2. But then you go further into the infrared, into the thermal infrared, not just the hot stuff, like there are thousands of degrees, but go down further. Then you can see through all of that debris, and presto, that second star shows up. It's a beautiful demonstration of the kind of science that you can do when you've got this infrared telescope out in space, and such a big one at that. We can take a look at all of the planetary nebulae we can. Some of them will have binary systems, some of them won't. It will directly tell us, eventually, with enough data, what our sun will produce 5 billion years from now. as it ejects its outer layers.
Amazing.
Wow. All right, that's intense. That one's intense. I like it though. It almost looks like an X-ray image or something
Yes.
like that.
See,
It looks like Shrek.
uh,
It looks like Shrek,
Shrek.
kind of.
Shrek!
Yeah, you don't see it on the right with his
Maybe an
mouth
Angry
and his
Bird.
nose.
Go home, donkey.
Where's
Got
the
the
donkey?
I don't
See, I was thinking it looks like a.
Shrek.
I was thinking it looks like a virus.
Ooh.
Yes. Yeah, I could see
Kind
that.
of looks like Rorschach off The Watchmen
Uh-huh.
a little bit. But
Oh, yes. Mm-hmm.
So-
The blotchy face mask.
Yeah, I just think it's amazing how so many times the microverse looks so much like the macroverse. It's just really fascinating to me.
It's true.
That's very
I was
true.
amazed by that as well. And what
Insightful.
what I think that means is that what we've thought about, well, like you said earlier, right? When you've got the early universe and the current universe and all of that connection in time, but it turns out there's also connection in space, because at the subatomic level, right, you have quantum mechanics, but once you rise above that to like the cellular level, the laws of physics as we understand them are very similar to the laws of physics that govern giant galaxies and stellar systems and things like that. So there are certain beauties, certain symmetries that come up. Things want to be spheres for some reason, right? And so they're spherical. Things want to spin, and so they look like disks, whether they're large or small. There are a lot of differences, but there are fundamental similarities too. Yeah, these kinds of pictures are what make me feel connected, not just out to the universe, but also to the lowliest creatures on Earth. I mean, we're all connected by the same natural laws.
Right. And if we can all start realizing that we all come from the same stuff, maybe we'll start being kinder to one another. Okay, the next
Amen.
one is WASP 96b, which we talked about
Yes.
already.
Yeah,
I
I
don't know if
jumped
there's
ahead
anything you wanted
because
to add to that. No, that's great. Is there anything
Right.
else you wanted to add to the
Well,
signature of water?
well, the picture in the background is the artist's conception, right? But so if you
okay, I
right,
missed that.
right. So the picture in front is the actual data. So you'd imagine is that the star that this WASP planet orbits is that bright thing in the upper corner. Imagine it shining through that reddish haze, and then that light coming through to the JWST, being absorbed and processed by it, broken down into its component colors in the infrared, completely invisible to our human eyes. And you see these bumps and wiggles that are sure signs, like they've been labeled. The scientists very kindly labeled them for us, but you see those bumps and wiggles. They're sure signs that there's water vapor out there. And the experts can even tell by the shapes of those bumps and wiggles whether the planet has a hazy atmosphere, whether it has a sharp-edged atmosphere, whether it has a hot or a cold atmosphere. It's amazing what you can learn from these spectra. And I have seen versions of this kind of spectrum for a long time. For many years, people have tried to do this with limited success. Mostly you just see grass. Those bumps and wiggles are not clear. They look kind of just barely, if you like squint real hard and do statistical analyses, you can say, yeah, there probably is a bump. But with this, that's not necessary. You just look at it and go, there's water vapor. There it is. And if somewhere else in that solar system, there's another planet that's like the Earth, and it's in a Goldilocks zone, and it probably has water vapor too. And then who knows what else it has.
Oh, yeah.
Yes. The science community is reveling right now in all of this glory.
We are dancing in the streets. We really are. Yeah.
Yeah.
CJ, you care if I go back to the Southern Ring Nebula real quick?
Nope, I don't care.
We're speaking with Dr. Lou, author of The Cosmos Explained, which you can pick up on Amazon, and host of the Luniverse podcast. Dr. Lou, I was wondering, could you tell us exactly what a nebula is?
Yes. A nebula is a blob of gas. It might have other stuff in it, but a nebula is a blob of gas. And then there are different kinds of nebula. This kind of nebula is a planetary nebula because when they were first discovered hundreds of years ago, astronomers thought they might be planets. They looked like fuzzy blobs. It was only many years later, in our modern times, that we had such good telescopes that we could detect that these are not planets, but they surround a dying star, much less planets do. There are star-forming nebula, such as the Carina Nebula, which we showed earlier, right, which talk about new stars forming in them. There are dark nebula, things that are cold and dense, and their temperatures are hundreds of degrees below 0 Fahrenheit. But you can't really see them, except sort of as holes in the sky, almost. They block things. So all kinds of different nebula happen. There's something called a reflection nebula. Some of the brightness you see in the Carina Nebula here in the background, you notice how there's like blue streaks and stuff, right?
Yep. Yes.
And then there are stars in the background. Right. When those stars in the background are lighting up the gas and the dust, sometimes they will bounce off of the dust grains. And the dust grains could be made up of not just, say, black carbon soot, but they could be crystals or little sheets of graphite or something like that. And they act like microscopic mirrors. And then when there are trillions upon trillions of them in the area that the light is shining, they act like this huge composite mirror, and then they flash this glare out toward humans and our ability to see them. So some of that's reflection nebula. You can see that too in the Pleiades, in the Seven Sisters. You can just look up in the sky. If you ever look with a pair of binoculars or something, you're like, hey, what's that fuzzy white light that surrounds those Seven Sisters in the sky? And that's the reflection nebula. So there's so many nebulae. Heck, there's even a super villain called a nebula. But that's a different story.
Oh. I'm going to have to look for that in the Seven Sisters.
Yeah, thank you. That was fascinating. I had no idea. I guarantee you that is a much better explanation than the glossary of my astronomy book.
Well, I'm sorry about that. I apologize.
No, in a great way.
All astronomers for not having done a good job in glossary. No, really. I mean, I know it's hard sometimes, right, to explain in a book or to write something technical in a way that can be understood by everybody. But we should always try. I mean, this stuff is so beautiful. It shouldn't be the sort of secret code that's, only we who are knowledgeable and have spent years of our lives thinking about this can enjoy. Everybody should have access to the universe. We are all pretty awesome, as awesome and as ordinary as every star in the sky.
I feel like everybody used to have access to the universe. Everybody used to look up to the stars to figure out their day and to chart their way and what have you. And now we just all look down at our phones. But that's a whole other thing that we won't get into. So the next one, SMACS 0723, or do we call that SMACS 0723? I'm not sure. Okay. So this one has the James Webb Space Telescope has produced the deepest and sharpest infrared image of the distant universe to date. This one is magnificent. I still can't believe it's real. Like I really can't get over that this is an actual. I totally just thought, okay, they sent back all these numbers and some artist made this on their computer. No, this is a real.
It's real. Every single one of those pixels. It has been processed so that we can understand it and visualize it, but they are real data from the universe itself. So how do we talk about this? Well, let me just first talk about what SMACS stands for, the SMACS part, okay? It's the SMA Cluster Survey. That's why it stands for SMACS, you see, SMACS. And of course, we astronomers, like everybody else, we try to find acronyms that are cute and we can say them quickly and things like that, right? So that's what SMACS is. And so this cluster of galaxies is what we're primarily looking at. Every one of those blotches there is some sort of astronomical object, and the vast majority of them are galaxies. But this particular field has clustered a whole bunch of them together, thousands of galaxies, all within about 1 million light years radius. All right, now, doesn't sound like a small space, but when we're talking billions of light years in space, right, 1 million or a few million light years across is actually pretty darn compact in order to hold thousands of galaxies. Now, you see that sort of multi-pointed star-like thing, right, in the very middle, right? There are a few other multi-pointed star-like things there too. Perhaps ironically, those things are not distant. They are objects. They're stars in our own galaxy. And we actually would rather they not be there because they've actually kind of obscured the space behind them. They're so bright that they've bounced all off of the different optical parts in the telescope, thus creating these multiple spikes. Okay, so if you ever see a 6-point or an 8-point spike thing in these pictures, it's because they're too bright and they've saturated and they've kind of like started making reflections inside the telescope. So as beautiful as those things are, look past them for just a moment, and you see behind them all these galaxies. Now, most of them are already billions of light years away, but you might see that there are some like weird streaks. They're kind of like round streaks. They're kind of reddish and yellowish as opposed to the galaxies that are more whitish that are in the cluster itself. And if you look real closely, you'll notice that, hey, these streaks kind of form a circle. They almost are like what you see if I look through the bottom of a beer stein, you know, and you see like you're looking at lights in the background and they're all swirly, right? They swirl around the center of the bottom of the beer stein or a wine glass or a shot glass, you know, choose your favorite beverage. And so the distortion that caused this is something called gravitational lensing. The collection of galaxies has within it and around it and among it dark matter. So much dark matter. In fact, this dark matter far outweighs the luminous matter you see in these galaxies. It's basically formed a lens, and it causes the light from behind it to come through it, just as if you're looking through that bottom of the beer stein. And you wind up getting this mug-like effect of things all being twisted and distorted. If we could try to decipher the twisting, like put it in reverse, we would actually see galaxies, just like the ones here, but further away and clearer. And so some of those objects back there, we think, are 13 billion light years away. And they've been magnified and distorted, shining through this SMACS cluster because of its preponderance of galaxies and dark matter that is collected together. So all things that are twisted and bent and in arc shapes and curves and things like that are literally twisted and distorted versions of galaxies seen from just about the beginning of the universe, more than 13 billion years ago.
Wow.
It's really remarkable.
And in this tiny little snippet of the universe, how many galaxies did you say you think there are? In just this little snippet? Thousands.
Just to get a sense,
Wow.
and this is in the it's expressed in certain of the stuff that NASA released, but this picture here, which contains thousands of galaxies, the actual space on the sky that it takes up is actually quite tiny. Someday, if you feel like it, take a penny and hold it at arm's length, way off like this. When your arm is straight and you're holding the penny, this patch of sky is the size of Abraham Lincoln's eye on that penny held at arm's length.
Wow.
Wow.
That is how big or how small this space is. So even that space alone, that many galaxies, each galaxy with billions of stars, each of those stars with the possibility of hosting planets. I mean, we got lots and lots and lots of company out there.
Yeah. That almost brings me to tears, honestly, like just thinking about it. So other than the images that we have seen today, how many more should we anticipate and when in the near future?
Well, the Hubble Space Telescope project, the James Webb, as you know, is the sort of the next generation of the Hubble Space Telescope, and they're all run by the Space Telescope Science Institute in Baltimore, Maryland. And NASA usually releases 1 or 2 interesting new images per month for the public.
Okay.
However, if you're not processing those for the public to view, the number of images are coming down. Right now is hundreds per day. Pictures are being taken 24/7 right now. Yeah, because the Hubble Space Telescope is orbiting the Earth, right? Every 90 minutes. It can only see outward half the time. The other half, it actually has to cover itself up so that the sun doesn't damage the optics. But the James Webb Space Telescope is out at the L2 Lagrange point with the Earth-Moon system. That means that it and the Moon and the Earth and the Sun and the James Webb Space Telescope are in a line, right? So you have this thing basically orbiting in such a way that with the sun shield up, right, the Earth is always between the sun and the telescope. So it does not have to wait for the orbit. It's just snapping pictures. And most of them will not be processed for public consumption, although they all could be. But you can expect many of them. I myself am very excited because I'm fortunate enough to be part of a project called Cosmos Web. And this is the first Treasury proposal being done by JWST, which means that for 270 hours, 11 full days and nights, the James Webb will be pointed at a single area in the sky, not just the size of Abraham Lincoln's eye on a penny, but the size of the penny itself. So it's huge by those standards. There will be not just thousands, there will be millions of galaxies in this range. This cosmos field, when I first started working with this back in 2003, 2004, we wrote the first Hubble Space Telescope proposals. It was the largest area ever observed by taking the Hubble Space Telescope and mosaicing it across the sky in as large a patch as possible. And now we'll be able to do it with JWST in the infrared. We're going to combine that information. We're going to learn more about the large-scale structure of the universe and dark matter distributions and galaxy distributions and stuff than pretty much any time in the history of astronomy. And I get to be part of that. And there will be thousands of images from that alone. I'm so excited.
Very
it's
exciting.
pretty awesome. Yeah. So it's a neat opportunity to be an astronomer.
Yeah.
I'm really loving it.
Yeah. I bet. So great. One last question about the JWST, then we'll move on. What would you say is the biggest takeaway from all of the images that we have seen so far? What's the most important takeaway, in your opinion?
Wow. Of course, every scientist you talk to has a different takeaway, right? But if I were to choose one
but we have you right now. So.
It is
the ultimate authority.
One takeaway I would say, you're too sweet. The one takeaway I would say is that when scientists and policymakers and the people, American, European, Asian, everybody, all get together and say, we want to learn something about the universe. We want to learn something cutting edge. We're not satisfied with just what we've been told over the years. We want to really know something. When we decide we want to do that, we can get something like this. We can find out about things in the universe that no one, even a few decades ago, could have ever imagined. I mean, we now are on the doorstep of really detecting planets that can host extraterrestrial life. We are on the cusp of being able to understand when galaxies first formed, just a short time after the Big Bang. When did the first stars form? When did the first black holes form? How do all these hugely cosmic and yet very basic life questions fit in, and how we are part of that universe? We've done that because for 25 years, a lot of dedicated people worked at it. A lot of policymakers said, this is worth it. This is worth our taxpayer funds. This is worth our time and energy to continue to work on this and to people all around the world to do this. And all of us said, we are willing to take a little bit of our collective energy as a society, as a nation, as a community, to do some of this stuff and see some of these things. These are the things that happen. And when this happens, we really can do just about anything we put our minds to. And our minds are blown, and these questions are being answered, and we just feel a little bit more connected with everything around us. We just understand that it's not just, dog eat dog civilization. It's not just, things that are rough. It's like the best music, the greatest art, the poetry, the things that make our souls sing. Science does that too, if we work at it. That's the big message I take away from these images, because the James Webb Space Telescope works, and it works so well. I can't even imagine what the next discoveries are going to be.
Yeah, I can't wait. I cannot wait. Well, this isn't even why we brought you on the show. We have some big fun things planned, but how could we pass up the opportunity to talk to you about just this breaking news? And it's so pertinent to what you do. So thank you for sharing your
thank you so much for having me and giving me the opportunity just to ramble about this. I mean, I'm loving the opportunity to share this with everybody. So thank you.
It's terrific. It's historic science right before our eyes.
It really is.
It is. We're living
Yeah, it's unbelievable.
All things unexplained.